Hello, class. We're going to try example number 3. So, this is on how to do systems. Okay, here we go. So the first thing that you do is draw your free body diagram. What we have here is smiley face guy pulling on the cord here, and it pulls on block M2, and M2 is attached to M1 by this cable with a tension in there to M1. And it says a 5 kilogram box M1 and a 15 kilogram box M2 is being pulled by a 60 Newton pull force. Draw both free body diagrams and find the acceleration of the blocks and the tension force. Okay, so draw the free body diagrams. Let's do them in red here. This will be free body diagram for M2, FBD for M2. M2 is what? M2 is 15 kilograms. I'm going to just write that up there too, just so I don't get mixed up here. And this is going to be the free body diagram for M1. And M1 is 5 kilograms. I'm trying to be careful that I don't get the masses mixed up here. So that's the free body diagram. So M2 has a pull force pulling it to the right. The pull force. Okay? It has a rope attached to it pulling back. And that's going to pull you back. Just imagine that you're on a toboggan and someone's pulling you forward, but you're reaching back and holding on to the next guy's toboggan behind you. And as you're being pulled forward, you still feel that tug backwards from the inertia of the guy behind you. And that's the tension force pulling you back, the tug force of the guy behind you pulling you back. There's a normal force pushing up on this. Beg your pardon?
Can that be counted as drag too?
No, there's no friction. If there was friction, we'd be adding another arrow. There's a normal force, the ground pushing up, and why is it pushing up on you? Is because you are being pulled down into the ground by gravity. But you're not sinking into the ground. Okay? Yes?
How do you know that there's something pulling back on you?
Because you can actually the question was, how do you know that there's a tension force pulling back on you? This rope has tension in it. That's what we're told. And tension is a force that's in two directions. Like yesterday's lesson, it pulls both directions. And it's the same force. So this, even though this block is pulling back on it, it pulls back on you. It's like an action-reaction force, the tension. Okay? Because, and the question is in the simplest form, there's a rope attached here, there's a rope attached here. So that means ropes can't push, so they have to pull. So there's a force pulling each direction here. Just translate those over to here. As soon as you see a rope there, as soon as you see an object sitting on a surface, you put a normal force. And as usual, if it's on the earth, there's a force of gravity. So let's do the M1 block here. There's a normal force because it's sitting on the surface. There's a force of gravity pulling down. And there's a tension force pulling it forward. There's our two free body diagrams. Now, we find the acceleration of the blocks in the system and the tension of the force. So we start off with the system. So because I'm starting with the system, I'll write down the word system. So the mass of the system is 20 kilograms. There's a pull force on a system, and that's 60 newtons. And when considering the system, we don't ever look at the tension in between blocks of the system. Why? Because they both push and pull and end up canceling out. every tension force between blocks of a system will always cancel out because one pulls one way and one pulls the other way, and they end up canceling each other out. So tensions, when we do systems, you'll never include tension forces in there. Okay, so we now write out Newton's second law. F net equals the sum of the forces, which equals ma. And the sum of the forces is just the pull force. There's no other forces. And it's the mass of the system, 20 kilograms, times the acceleration. This is 60 newtons equals 20 kilograms times A. So the acceleration is going to equal 60 newtons divided by 20 kilograms, which is 3 meters per second squared. Newtons per kilogram is equivalent in units, equivalent to meters per second squared. We've talked about that before. So the acceleration of the system is 3 meters per second. At that point, I'm going to box that out because that's one of my answers. It says find the acceleration of the system and the tension force. We have found the acceleration of the system. Next, we look at one of the boxes. Okay, so one of the boxes, right underneath this box, I will write down the sum of the forces is equal to F net, which equals ma. There's only one force in the direction of motion. Now I'm going to ruin my free body diagrams here for a second and then undo it because I don't want to keep it that way. So, but the direction of motion is this way. You don't do that to your free body diagrams. But the ones that are highlighted yellow are the ones that we are interested in. Everything else, they balance out and become zero because the direction of the acceleration is to the right. We're told that right up here. Okay, so the only force that's acting in the direction of motion in this block over here is tension. I'm just going to undo that to get rid of that line. We don't want to ruin our free body diagrams that way. So the only force is tension, and that has to equal ma. Now we're only dealing with one block now. We're not doing the system. We're dealing with just this block. So the tension is equal to the mass of that block. The mass of that block is 5 kilograms. What's the acceleration of this block? 3 meters per second squared. So the tension here has to be 15 newtons. Yay, I'm done. Go home. Okay. Well, you're done, but as I always stated at the beginning of this lesson, many times, is that there's a check. The check is doing the next block. The check will always be doing the last block. So why would I know the tension, I know the acceleration. Well, let's calculate and do this as a check. And what will I calculate? I will pretend I don't know the tension. I'll calculate the tension again. And hopefully I'll get 15 newtons. Okay? This is the direction of motion. Those are the only forces that we're interested in. I'm going to delete that yellow arrow. Those are the forces that we're interested in because that's the direction of motion. So, the sum of the forces is equal to F net equals ma. The forces, there's two here now. F pull minus the tension. And that has to equal ma. The pull is 60 newtons. The tension is what we're trying to calculate. Mass is 15 kilograms. What's the acceleration? 3. So 60 minus tension is equal to 45. That means tension is equal to 15. And I don't box this one off because this is a check. It's just, this is where I solved it. This is where I checked it. And then I draw this smiley face. And I put a couple check marks and I write down, yeah, it checks out. So I drew the free body diagrams, I calculated the system, I used Newton's second law once here, and ignored all tensions, calculated the acceleration of the system. And then I went over here and calculated for one box, Newton's second law, the mass is only of that box. I use the acceleration I calculate the tension. I do a check. I tell the person who's marking it or looking at the work that I'm checking for tension, the last thing I just calculated. I write down Newton's second law. I add up the forces that are acting on it, equals to MA. I write it down, calculate it, I check it, I draw my happy face, and I'm very happy. Let me just save this for a second.